probably one of the oldest time series databases that have been around since the 1990s. And for me personally, it was their architecture was heavily influenced the design of the HStore system, even though HStore was not a time series database. So again, part of what the seminar series is about is try to understand what time series databases are and why didn't KDB solve this problem 20 years ago. So Fintan has been with KDB for 12 years now, and prior to that he did his undergrad at Trinity College in Ireland and has a BS with first class in computer science and computer engineering. So we're really happy to have Fintan here today, and take it away.
Thank you very much, Andy. It's nice to meet you all. Thanks to everybody at CMU here on behalf of KX and myself. It's a great honor to speak here. Thanks for the hospitality you've all shown. So hopefully I won't bore you all too much today. Let me know if you can't hear me, by the way. I usually try and speak as loud as I can, but if you can't hear me down the back, just let me know. So these are just a couple of boring company slides at the beginning, just to get out of the way. Just a little bit about KX. We were founded in 1993. We're a subsidiary of an Irish company by the name of First Derivatives. So we're publicly traded on the London Stock Exchange. We have about 2,000 plus employees worldwide. We've got a big global presence. Here are some of our customers and partners. We've mostly been involved in the financial services, and then in recent years we've branched out into other industries as well, so telco, IoT, you name it, anything that needs time series. There's nothing specific to our technology that's to finance. It just so happens that that was the industry that we grew out of that had the need for big data back then. So here's just a sample of some of the companies. But first of all, I kind of wanted to go back and do a bit of a history lesson and just kind of show kind of the ideas and the methodologies that came in to KX and KDB+. So this is just a funny slide to just showing, here we go back in time. And so it kind of all goes back to this gentleman here. His name is Kenneth Iverson. He's a Canadian, and he worked at IBM. He's an IBM fellow, and he was at Harvard as well. And he started a language by the name of APL. So the idea being that everything was a vector programming language. Everything was vectors. You thought of everything in lists. And what he wanted to do was basically create a programming language that was as near to the scientific notation as possible. And so something that scientists and mathematicians could kind of write out as near to what kind of they were learning. And he basically came up with this Turing lecture-winning paper called Notation as a Tool of Thought. And if you haven't read it, I'd highly recommend reading it. It's just a very, very nice and elegant way of how to express ideas, and it kind of all harkens back to this vector programming language. One of the things with APL was that it had its own keyboard, so it had this weird kind of hieroglyphic style language. So for some people it was quite difficult to understand. So here's an example of APL code using the how to find prime numbers, for example. So here's what it looked like. So if you're not familiar with the APL language, this can kind of be a little bit difficult to understand. But the idea being is that it achieved a lot within one relatively short line of code. And then on came along the founder of KX, a gentleman by the name of Arthur Whitney. So he was effectively Ken's protege. He was also a fellow Canadian, so he grew up with Ken very much as a father figure in his life. And he basically learned from Ken, and he created a prototype language called A and A+, and then a language called J, which he worked on with Ken Iverson. And then he also basically came up with a language called K, which is the predecessor to our current language Q. So what it was in essence was an APL style language, but just using the ASCII character set rather than say the APL kind of this weird hieroglyphic kind of character set. So he's trying to bring it slowly into kind of the more modern understanding and the QWERTY style keyboard solutions. So this was the K language. So then what we wanted to do is, it was purely a K language. That's what KX started out as, was basically this functional kind of programming language company. And then eventually we got into building a columnar database. So this is a sample from the Book of Kells here. That's from my alma mater, Trinity College. And the idea here is that a lot of these lists and vector notations that we came across in the APL language, they just translated very, very nicely to the columnar structure. And of course now in recent years, columnar databases have become very, very sexy. And people doing based databases have been left behind. So you see row-based databases are somewhat of a thing in the past. There's still a place for them somewhere, certainly, but it's kind of everything has moved more towards columnar now with the increase in big data. So the K language then came to KDB, which was the first iteration of the database, and then we have the current iteration of the database, which came about 2003, called KDB+. But people use the names kind of interchangeably. A lot of the data models are in essence the same. So what is Kdb Plus then? So Kdb Plus it's a unified columnar database and programming system. So it's not just a database. It's not like your traditional sort of database server and application server where you push data back and forth between the two. It's a fully Turing complete programming system, and we'll get into the language and the Q language that sits on top of it a little later. So I really just want to emphasize that point, that it's not just traditional database that we extract the data from it and we do our analysis elsewhere. With this, we can do the analysis directly on the data. So it follows the Lambda architecture, and obviously that's become quite prevalent in the recent years, Twitter and stuff like that. So, but finance has kind of been using the Lambda architecture since kind of the late 70s and the 80s with the advent of high-frequency trading. So the idea being that you had your streaming data, your real-time or in-memory data, and your historical data being used in the one platform with the one programming language. So you compare that to say like this Hadoop style of Frankenstein monster where you use about 17 different technologies for the different pieces, and they don't necessarily integrate together very, very well. Whereas with us, we have the one database paradigm and the one programming language that kind of knits everything together. So in some ways, it's kind of a one-stop shop, or somewhat like a Primanti's Brothers sandwich where you get the fries, the meat, and the bread in one. So what it's all about basically is in database analytics. So the idea being where you bring the analytics to the database. So as I mentioned, not like your traditional analytics server and database server. It also supports joins, so it supports all the standard SQL-like joins, and then we'll go on to some time series joins that it supports later as well. And the nice thing as well is that it's a 500 kilobyte binary, so it fits almost entirely inside the L1 or L2 cache of a modern machine. So very, very short code paths, so it just leaves more space for the data essentially. So it's not like a lot of the other big data solutions nowadays that have gigabyte install paths. This is a very, very short code size.
Wait, so the entire database system is 500 kilobytes?
Yep.
Everything?
Yep. Exactly, yeah. So if you download, we have a free version that you can download. You go to our website. I'll have a slide about that later on, and you can download it right there and then. You can install it on your Raspberry Pi or whatever it might be. So it's quite nice. So this is a very typical KDB Plus architecture diagram. So this is by no means, the end-all solution, but it's a kind of a reference architecture, as it were. So you got your data coming in on the left. So that could be coming from any streaming source, a stock exchange, an internal trading execution engine. It could be even from a Fitbit device, a sensor, or a smart meter, or whatever it may be. And that's typically parsed using a feed handler, which is usually written in the compile language for performance purposes. And then all of these blue boxes here that you see residing in memory are typically written in our Q programming language that I'll talk about later. So they're all just, there's no specialist libraries here written in C++. This is all written in the one language. So first of all, the data comes into our events engine, or sometimes in finance it's called a ticker plant. And what that does is basically it distributes data downstream. So it's a data distribution engine. But the first thing it does is it logs its messages down to this transaction log file here on disk. So this is for recovery purposes. So if any of your downstream processes go down for whatever reason, you can get full replication and full recovery from this transaction log file. So then the simplest example of a subscriber to this events engine would be what we call the real-time database, or the RDB. So what that does is it basically just subscribes for everything. So it opens a fire hose and just gets all of the data, takes the data and inserts it into in-memory tables. So it's a pretty simple process in many ways. Not terribly CPU intensive, but it can be quite memory intensive as the pages grow and grow throughout the day. But then if you've got one very specific calculation that you want to run, or dedicated engines, like I want to get the volume weighted average price for these particular stocks, or I want to get the average kilowatt hour usage for this particular zip code of smart meters, and then you can set up what we call a streaming query engine. And this, once again, these can be written in the Q language. They can also be written in other languages as well that can subscribe to Q. So you can spin up multiples of these, and say for the VWAP pricing engine in finance, for example, and then you will only subscribe for a subset of the data, maybe trade trade data, and maybe only for the ticker symbols that we're trading in our portfolio. So it typically gets a lot less data, but then when it gets the data, it starts running calculations on the fly, and so it's doing the calculations as the data comes in. So it's much more CPU intensive, but it's typically a lot less memory intensive, as it might just store maybe one record per subscription. So it's way less memory, but way more CPU. So kind of the reverse type of profile from the real-time database engine. And then what typically happens at end of day or whatever the pre-configured interval might be, the events engine will send a message to its subscribers and say, it's now like end of day or end of session or whatever it might be. And in the case of the real-time database, what it does is it basically purges its contents down to what we call the historical database. And then the historical database, you create a new shard or a new partition on disk for that day. So basically all of your current day's data is running in memory, so it's very, very fast access, and then your older data is running on disk then in your historical database process. And then if we go on to the next slide, you'll kind of see that essentially everything is just column arrays, and the way the data then is persisted down to disk is essentially the same structure, albeit it's just on disk. So it's essentially just an image of the data in memory on disk. So the historical database can take advantage of the operating system file cache. So when I go back and I query yesterday's data, it will get page faulted into memory, and then any subsequent queries will get near in-memory performance. And that's all done at the OS level. You don't have to care about that as the end user. So the data model is essentially the same both in memory and on disk. It follows this columnar or vector style structure. So you see the data model, holds quite well. It's a very simplified data model, and whether you're querying the streaming engine, the in-memory engine, or the on-disk engine, the queries look almost exactly the same. It's a select style syntax. We'll get onto that in a little bit, though. So we support many different data types. You want to be flexible in the database itself. And so here are just some of the database data types. We've got Boolean types, we've got numeric types, and we've got character types, and we've got a symbol data type, which is quite important. And we've got a GUID, which is basically a UUID data type as well. So if you've got highly unique data, you can get very fast in search performance on that. We support enumerated data types, and then we also support dictionaries, tables, key tables, and functions as first-class data types. And there are other data types as well. We also support time series data types, so seeing as we're talking about time series today, and we have a data type for date, time, minute, second, month, date, time span, and timestamp, which are both nanosecond data types. And you can convert between these time series data types very quickly on the fly as well. So it means you can store your time series data in its most granular form, but then if you want to do bucketing or something like that, you can convert between those data types on the fly very, very easily. So you don't need to store your data down in different resolutions. You can just store it once in its most granular form, and then you can do roll-ups very fast. So then on top of this, then you got this very nice platform, but you want to put a nice elegant language on top, something that's very expressive. So with that, then what we came up with was the current language, which is called the Q language. And so here are just some of the aspects of the Q language. First of all, it's a functional language. So it comes with 200 plus functions out of box. So it has all of the standard database functions, like your aggregate functions, like first, max, min, last, etc. And then it also has matrix functions, so matrix multiplication, inversion. It also has trigonometric functions, geometric functions, moving average, weighted average, moving sum, weighted sum. So a ton of different functions. But you can also create your own functions as well and then plug them into the database. So you're not just restricted to those 220 or so functions. It's also an array / vector programming language. So that, what that means is that basically most of the functions that you run are array or vector-based functions. So you get rid of a lot of the clunky control structures that you have in other programming languages. Like you typically don't have for loops, while loops, do loops. So that actually just reduces your code base pretty significantly, and it just lends to neater, more elegant code. But it also has a query language in it as well, and it's all in the one language. It's not like PL SQL and say SQL, where it's two completely separate paradigms. And we have select statements, update statements, delete statements. So it's kind of like a superset of SQL. And you can merge the functions into your queries as well. So you can create your own function and then plug that into the query. And it's also an interpreted environment, as we'll see in a second. So you can type the query and get the result back straight away. So it's very nice. It kind of changes the methodology with which people would approach maybe like compiled like environments, where they have to compile some piece of code, go off, get a coffee, come back, and then it will be ready to run. With KDB, you can start prototyping. So it's very kind of changes the way the developer kind of thinks when they're actually running queries and creating a lot of this type of stuff. So then it's also a language for time series as well. So it has a lot of time series functions and joins. So there's some functions that we'll see a little later, xbar, which is for bucketing or binning of data. So you can start creating like uniform buckets of data, or you can create non-uniform buckets as well. And we also have two specific bitemporal joins, one of which is called an as-of join and another which is called a window join, and I'll get onto them a little later as well. You can also do temporal arithmetic, like you can add from a date, subtract from a date, add seconds, subtract seconds. So you can start doing a lot of like very nice, analysis using time series data. So it fits very nicely with the KDB Plus model and the Q database. So then, there's many different attributes that come with KDB Plus as well, and attributes is the word that we kind of have for the concept of indices that you'd have in other traditional programming languages. So we support 4 different types of attributes, and they're just denoted by you put this backtick and then a pound after it. So the backtick S pound is for assorted attributes, so that means your search algorithm will change if a field or a table or a column is sorted on a given, and you can have sorted on an entire table, or you can have it on a dictionary, or you can have it on any of these data types. Then there's parted, and what parted basically means is within a given partition, you have a step function, so your data within a given shard or a partition on disk is held contiguously. And then we have a unique value, so obviously if you're doing that needle in a haystack style query on an ID column or something like that, you get very fast performance. And then we have grouped, which is like a more traditional index where you have a hash map style index that you'd have built in a traditional database. So we have these 4 different types of attributes, and they can change the performance of a query very, very drastically in terms of you can get way, way faster performance where you can take advantage of these. And some of them are better placed for in-memory data structures, and then some of these attributes are better placed for on-disk data structures. So you got some flexibility then. But it's not like other databases where a lot of the time they'll just index every single column, and then all of a sudden there's this huge memory overhead. And you typically only tend to put these attributes on maybe 1 or 2 columns out of your table. So you use these quite sparingly, but you'll find the performance is very, very good.
These are attributes that you're defining when you create the table.
Exactly. Yeah. So you'll add these, and then when data's coming in, say to the grouped attribute in memory, it will maintain that attribute. Yeah. So then, of course, we can take advantage of parallelization. Obviously, that's a big thing nowadays as we're getting into multi-core architectures and multi-machine architectures. You want to be able to take advantage of these types of things. So from a vertical scaling perspective, we have the ability to do multi-threading. All of the multi-threading is done under the hood, so it's abstracted away from the end user. You just start off your process with multiple threads. And one of the nice things that we put in more recently is we've actually gotten rid of serialization in between these threads. So that means then you can get really much better performance with these multi-threaded queries. And then we automatically distribute the queries across the CPU core. So there's no like heavy, clunky multi-threaded API on top of the database that you have to learn. It's very, very simple, and it's kind of abstracted away from the end user. So if there's certain query patterns that are just automatically parallelizable, KDB Plus will parallelize them. So that's how we scale up. And that's quite popular in finance, where they got data coming in throughout the day and they're trading on that data, so they want really, really fast access. So they usually tend to scale up by adding like more memory and more cores rather than more machines, which you get kind of when you go onto so it's an East Coast versus West Coast thing. It's not quite as cool as the rap battles in the 90s, but you get the idea. And then we've got horizontal scaling then as well. So that's for more historical type of workloads, like big historical research queries or backtesting and stuff like that, where you're going through petabytes of historical data, or maybe say for regulatory reports where you might need to keep 5+ years worth of trading data for reporting purposes to the authorities. And for that, then we can do a multi-processing model. So we're not just restricted to multi-threading. We can do multi-processing. So we've got master-slave setup, and then you can set up nice failover and stuff like that as well. And once again, this will automatically distribute the queries over the multiple hosts as well. So they don't even have to be within the same machine. And even within one database, you can take advantage of tiered storage as well. So that's nice too. We also exploit some of the Intel vector instruction sets. So if you're running on some of the latest Intel machines, you can take advantage of those wider register widths that we have. And it obviously lends itself quite well to our data model of supporting vectors. So we can automatically parallelize some of those calculations for some of the primitive functions. Other than that, though, KDB Plus itself is written almost entirely in ANSI C. So it's hence the 500 kilobyte executable. We also support native MapReduce. MapReduce has been around forever. Even though some of these West Coast companies like to think they invented it. APL has basically had MapReduce style semantics way back in the 50s in the mainframe days. So we have MapReduce style built in, so whether you're doing the multi-threading or multi-processing model, and we can take advantage of that. And then we get on to compression. Just take a quick sip of water and let this slide sink in. So we support compression then. So we support compression from a few different viewpoints. So built inside the executable isn't just a database, but we also have a WebSocket server and client, and we also have a HTTP server, so all inside that 500 kilobyte executable. So it's a fully compliant WebSocket server, and it supports the WebSocket compression standard. And the second type of compression is in-flight compression between hosts. So if you're sending large amounts of data, say from machine A to machine B, you can compress that data before you send it over the wire. So you get better bang for your buck in terms of bandwidth. And then we also support on-disk compression, which of course is very important when you're storing, years and petabytes worth of, financial market data or streaming sensor data, etc. So we support 4 different compression algorithms. The first is our own internal algorithm, which is the same algorithm we use for the in-flight compression. The second is gzip, and then we support Google Snappy, and then we support the LZ compression algorithm. We have that in our latest beta version, so that will hopefully go into production in the next version later next year. And you can obviously offload some of this to hardware compression boards as well. So Kdb Plus has very, very few library dependencies. The only library dependencies we have are actually on these compression libraries. Everything else just uses standard OS system calls, so it's very, very close to bare metal, which is why you get the very, very fast performance.
Can you say a little bit about what Kdb's compression algorithm actually does compared to Snappy or LZ4?
So it was basically it doesn't compress quite as well, but it was all built about speed really. So it was built more towards speed, and then specifically it was to doing the deltas on time series data. So that was one of the very important things. So obviously when you're doing nanosecond time stamping, you're getting very granular time stamping, so they don't compress as well. So speed and time series is what was kind of more optimized towards. So yeah, the gzip, for example, you get way better compression, but then the decompression is going to be a lot slower. So then we get on to security. So obviously, this is one of my favorite little Twitter memes that I've seen. So we support encryption for in-flight data. So we support SSL and TLS encryption. You can do row level. You can do columnar level security as well. We don't support on-disk encryption at this point, but all of our data that's on disk is typically just in file and folder format. So we just can rely on the OS file system to take advantage of the encryption there. But it's something that we may take a look at. Then in terms of APIs, then we want to be able to connect to a lot of these, cool different tools that are out there nowadays. Not everybody necessarily needs to use a Q language. You can use other libraries as well, but still take advantage of the power of Kdb Plus. So here's just a few examples. There are many, many more. So if you're, say, interfacing with other database solutions or maybe interfacing with the Tableau front end, we have ODBC and JDBC libraries. And then we've got native libraries for, C, C++, Java, Python, R, Kafka, etc. And these libraries typically work in one of 2 ways. They either just open TCP/IP socket connections, push data back and forth, or another nice thing that you can do with Kdb Plus is you can actually embed shared objects. So you can load shared objects into the same memory space. So that's in fact how the Python and R APIs work, where you can actually have the Python interpreter and the Q interpreter running in the same memory space. So you could say run a NumPy function or routine on Kdb Plus data, or conversely do maybe a pandas routine or say the Kdb function on a pandas data frame. So that's quite nice, because then you don't need to copy data back and forth, and you don't need to go through the TCP/IP stack. You can kind of avoid that. So then we can move on, and then we can actually kind of see it in action. So we'll have a look at our demo environment. So you'll see it for your very first time, hopefully. Or has anybody actually played with Kdb Plus here before? No? Okay, cool. So the demo environment that I have here, it's 31 terabytes in total. So it's actually real New York Stock Exchange data. It's from January of 2013 onwards, up until yesterday, in fact. We load it on a nightly basis. It has about 1.3 trillion records. It has the raw trade and quote data, like the raw message data that comes in, so very, very large tables. It has some derived data as well, so for each date and each stock, it has the open, high, low, and close pre-calculated. The machine that we're running on has about a ½ terabyte of RAM, but to be honest, most of the queries that we're running here are on disk, so we actually use very little memory, so we wouldn't even need that much in practice for the queries we're going to run. It runs on 8 Haswell cores. We typically turn off hyperthreading. They're 3.5 gigahertz, they're pretty fast clocked, and the queries are run fresh from disk, so it's all spinning disk as well. There's no SSDs or NVMEs running on this drive, albeit they're 14K RPM, so pretty fast.
Why do you turn off the hyperthreading?
Sure.
Why?
Why do we turn off the hyperthreading? Well, it's one of those things that traditionally we used to, just because the hyperthread used to get in the way, because we'd be able to drive the CPU so fast that we found that the hyperthread would actually impact somewhat. But to be honest, more and more nowadays we find in some cases we turn it on and it has negligible effect, and sometimes might even increase performance. So the lines with that have now been somewhat blurred. So I turn off the PowerPoint, I guess. Okay, so here we are in the Q environment here. So as you can see, it can do basic math. We do 1 + 2, it does return 3. So we're doing good. You can create lists very easily. So you can do A = 1, 2, 3, 4. And then you can do, say, sum of A. And we can do sums of A, which gives me the running sum. So you got a lot of these different types of functions. I can create a table very easily. So I'm going to create a simple table T, which has 2 columns. A = 1, 2, 3, B = to, say, A, B, and C, and then I'll create a third column C, which is going to be 4, 5, and 6. So here I go, I have my simple table here. I can do select sum of A from T. So you can start creating tables and start creating these data structures very quickly and very easily. I can start creating functions then. I'll create my own function, and I'm just using these parentheses, and I can just do x + y for my 2 input parameters. So now I'll just clear the screen. So now we got our function, and now I can apply that directly into the query. So I can do, say, select func, and then I can do the columns A and C from T. And you see we get the result back here. So we sum the values from those tables. Likewise, I can create a second function. So you can have functions inside of queries, but you can also have queries inside of functions. So I can do, say, select from T where, say, A = to x, where x is our input parameter. And now I can do func of 2 and just pass in the value for, say, 2. And it will return that corresponding row from the database.
X is the input?
Pardon?
The variable x is the input? How did the system know that x was the input?
Oh, so yeah, so we have the concept of implicit parameters, so you can pass up to 3 implicit parameters, x for the first, y for the second, and z for the third. And then you can also put in explicit parameters as well, and you can do that very easily. See, I'll create func3 here, and I'll put in my param will be just called param. And then I can just explicitly put it in here just inside the declaration. So if you want to make maybe more readable code rather than have x's and y's and z's, I can do this. So then I can just change this around and just do func3 and pass in 2, and you see the result comes back. So you see the idea here where you can have queries inside functions and functions inside queries. So it all melts in very, very nicely. So now we'll go into the database. We're actually in the database process that we're currently running. So you see that there's very large tables here. You can do a simple count. So count returns very, very fast, whereas doing a count on a table in another database typically takes a long amount of time. So you see there's about 771 billion records in this table, so it's quite a large table. So it has how many dates in the table? It has 1,213 days. The last date, just to show you it has real data, is yesterday's date. The first date is from, I think, January 2nd of 2013. Yep. So you can see you can start doing counts. So the first query I'm going to run is against this relatively small table, a daily table. So it's for each date and each ticker symbol. It has open, high, low, and close. So I'll just copy the query across first. Hopefully my copy-paste skills will be good. So this is a pretty simple SQL-like statement. First of all, I'm just going to put a \t in front of the query, and what this does is it actually times the query, and it returns the amount of time taken in milliseconds. So as you see, this statement here is doing a select the date, the open, the high, the low, and the close from this daily table where the symbol equals Apple. So this is a pretty simple, if you're used to an SQL database, isn't too much of a jump in terms of the syntax. It's relatively straightforward. So I'll run this. and it will take about 530 milliseconds. So this is the number of milliseconds taken to execute the query. I'll run it a second time, and you'll see now the second time you see this effect of caching, so it's cached the data in memory, so it's about like 10, 15 times faster. Excuse me.
What does that backtick mean?
So this backtick, this is what we call our symbol data type in the Q language. So this is like a varchar in standard SQL databases. So we just denote it by the backtick because we just like to use as little code as possible. So if we can drop one character rather than having an enclosing backtick. So yeah, so this is the specific symbol data type, which is essentially an interned character string. So it basically means it's one object rather than say 4 characters as a vector. So that's, yeah, it's a special data type in KDB+. So now if I just run that query, you'll just see what it looks like. So it just looks like a table that's returned. So we return the data. So obviously it returns, that data in a pretty fast time. But, it's not a huge amount of data. What was it? About, 9 million plus records. So large, but not very, very large. So we want to do queries over billions of records. So the next query I'm going to run is I'm going to get the open, the high, the low, and the close, but I'm going to actually do it from the raw data. So I'm going to actually run these aggregate functions on our trade table. So I'll just show, and we're going to bucket it up. So we're going to group the data by date and then by 5-minute bucket. So we're going to do 2 levels of bucketing. So first of all, I'm going to time it again just so you see it. But what we're doing here is we're selecting the open, which we're going to define as the first price. So this is just the same as doing first price as open. And then the high is going to be the maximum price. The low is going to be the minimum price. And the close is going to be the last price. And then because KDB+ is a time series database and columnar, it's already ordered by definition. It's not like an SQL row-based database where it doesn't infer order. So that means we just move the group by and order by inside the select statement, and we call it the by clause. So we aggregate the data by date and then by 5-minute interval. So the time column that's in our data base is stored to millisecond resolution. So by doing time.minute, we automatically do the conversion from this millisecond timestamping to the minute timestamp. And then this xbar function that I showed earlier, it does the bucketing or binning of the data. And then the number to the left-hand side just shows the resolution of that bucket. So we want it in 5-minute buckets. So we aggregate the data by date and then by 5 minutes. And then it's from our trade data, which is the raw message data for each and every trade. And then we're doing that for where the date is within the last 7 days. So this .z.d variable is just for the current day, basically. So it just means today. So today minus 7, so you see that temporal arithmetic, and today. And then the symbol equals Apple, and then the time is within. So the within statement is like doing between X and Y. So then it's between 9:30 and 4 o'clock, which are the opening hours of the New York Stock Exchange. Okay, so I'll quickly just run that query. So we're aggregating over 7 days worth of data, and then we're bucketing it, and it's taken 98 milliseconds to run that query. So we'll run it again, and you'll see now it takes about 8 times faster, and the second time due to this caching effect. So I'll quickly just show you the data. So you see now what this returns is a keyed table, because remember we've aggregated the data by date and then by 5-minute bucket. So you see that we've got nice 5-minute uniform buckets in between. And then we've got our open, our high, and our low, and our close. And so basically this means that between 9:30 and 9:34.59.99999, and this was the open price, etc., etc. So we do this bucketing and binning very, very quickly. And then we can change, we can go, say, if we want to do a 30-second window instead of a 5-minute window, we can go then and we can change that. So just to show you I'm not, making up anything, you can do that. And then you see, you see the idea, it's overflowing on just the console here, but you see the idea here, it's date, and now you see we get this second data type. So you can start doing this bucketing and binning of the data very, very easily. You see the queries return very, very fast, so if you wanted to, does anybody want to give me a stock that they want to see? MDB. Is that in the NISE? I'm trying to think what stock that is. There we go. See the result book comes back pretty much straight away.
That's Mongo.
That's Mongo. Yeah. Oh yeah, they just came up. That's yeah. Excellent. The enemy.
That's on video. You said that, not me.
Yeah, exactly. So you see, these are the real tick by tick data. So now what we want to do is I want to show you one of these, what we call the bitemporal queries. And so what I mean by that is when we're joining two different time series. So if you think about it in practice in the world of finance, but this can be obviously in any other industry. In the finance world, you got your trading data. So you got your broker saying, I want to buy and sell this stock. So they're giving you the two prices. And they'll give you that, and you'll store it in your quote table at say 10 a.m. And then maybe you want to trade on that, but maybe you mightn't trade until like a few seconds later or something like that. So then you've got a trade record and you've got a quote record, but they don't necessarily have the same time. So if you try and join the data using one of these like standard SQL joins, you'll get a mismatch because they're not exactly time aligned. And so what we've built is we've built a few different types of time series joins, and one of which I'll show you today. One of which is called the as of join. And what the as of join does is it will take that quote or that trade record from your trade table at say 10:02, and it will do a look back into your trade table and try and find, or the quote table rather. And if it can't find a quote record at 10:02, what it does is it looks back in time then, and it finds the last available value or the value that's prevailing as of that time. So that's a function that's built directly into the Q language. Actually, I'll just go back to the last query and I'll just show you the number of records we were actually aggregating over when we ran that aggregation. So we aggregated over 745,000 records in just over, I think it was 18 milliseconds. So you can see just the sort of speed of the query that you can get there. But yeah, I'll go back to the as of join, so sorry for that digression. And I'll run this as of join, so I'll just do the \t. So this as of join is just a function, so you see this functional syntax with the square parentheses. And the as of join takes 3 parameters. And the first parameter is the field or the column that we're joining the data on. So that's this backtick time. And then we have the semicolon separating the arguments. And the second argument then is a table that we're going to do the lookup from. So we're going to select the time and the price from our trade table, where the date is the last date. The symbol equals Apple, and the time is within 9:30 and 4 p.m. And then the last parameter is a table that we're going to do the lookup into, which is the quote table, or the NBBO, which just means National Best Bid and Offer, which means the best quote available as of that time. So we're selecting the time, the bid, and the ask from our NBBO table, where the date is the last date, and the symbol equals Apple, and the time is within that window. So I run that query, and it takes 87 milliseconds to run, and I'll run it again. You see it takes about 4 times faster. And obviously the caching effect isn't as noticeable this time, and that's because we've already actually cached some of that trade data in the prior query. So you see that the caching isn't quite as accentuated in the second query. So what I'll do now is I'll actually just show you what the data looks like.
So this is doing a join between 2 tables.
Yep.
And you write the join as 2 separate queries.
Yep.
Okay.
So it's 2 queries, and then it's joining based on the time column. So the time that it shows here is actually the time off of our trade record. So the table in the second, or the left-hand side table, as it were. And then the price, this is the price that was traded, and then this is the bid and the offer. And the beginning of the day, there's no bid and offer because it probably became just before that 9:30 offering. So this is the prevailing bid and the prevailing ask. So what I could do is I can maybe say then, you might ask, well, why don't you show the quote time as well? So the as of join actually suppresses the secondary time, but you can just get over that easily by just duplicating the time column and just creating a column called Q time, and that will just duplicate that column. And now it will show that. So if we look down through the records, and if we look at this record here, you'll notice that the time off of the trade actually happens 1 millisecond after that actual quote came in. So you see that the ability to do this, it effectively does a binary search back in time and to find the last available value. So you get very, very fast performance. So I'll just show you, like.
Is there a way to show the query plan for that query? Like, can you see it from the terminal?
Oh yeah. So there we go. So it took 20 milliseconds to run that.
You do explain in SQL to see actually the query plan tree that actually used to execute?
No, we don't have anything. Well, we do have a profiler, but it's a separate library you have to load in. I don't have it loaded in here though, but yeah, I could certainly send you information on that.
Is it doing like a hash join? Like what's the join algorithm for this?
Yeah, so it does a binary search lookup, kind of like a hash type of join, back in time on the table. So it cuts off basically as of that time and goes back in. And because of the way we order the data on disk and the way we have the data contiguously held on a given symbol but ordered by time, it actually can just do the join a bit faster back in time. So as you see, it does about 130,000 plus joins in 20 milliseconds, or searches rather, and joins, I guess. So that's the as of join concept. And then there's another version, a more generalized version of the as of join, which is called a window join. And there's an extra parameter that you can specify where you can have a window of time. So you could have something like, say, 2 seconds before an event or 1 second after an event. Say within that 3-second window, then I want to get, say, the average price or the first price or the last price. So that's a more generalized version of this as of join. The as of join is a very specific version where it just gets that last value as of that time. So I'll go back to my slides now.
Question?
Yep.
So based on what you said, it seems like it's optimized for joining on time.
That particular join is optimized for joining on time, but we do support like left join, inner join. We also have a join called a plus join as well, which actually adds numbers. So we support like the standard SQL joins as well. We just have these specific time series joins too. And there's also variants of the as of join and the window join for whether you include, the end of the window or you exclude it, whether it's closed intervals or open intervals. So there are some, so there's AJ0 and WJ1, for example. So just, yeah. So then just in closing, just to show a few more resources. We've done quite a few benchmarks over the years, and 2 particular benchmarks that we've done we show here. One is called a stack benchmark. So they're called the Securities Technology Analysis Center. They do a lot of financial benchmarks, so financial fintech benchmarks. And one of the benchmarks that we're involved with there is called the M3 benchmark. And what's nice about this is that it's run on a variety of different hardware stacks, but they have databases of 3 different sizes, and they run 17 different analytic tests. But they actually run them in their lab, so it's not like it's all independently audited and verified. So it's not like somebody that's cooking their own books and making something nice for the marketing department. These are actually real audited and verified figures, and we've been chosen as the database of choice for I think about 95 or 98% of those particular benchmarks. We hold basically all of the records there, so it's really nice to kind of show that, because benchmarks you kind of always have to take a little bit with a pinch of salt. But another nice thing about the stack benchmarks as well is that the actual financial institutions themselves come together and they come up with the benchmarks themselves, so it's not like one of these pointless database benchmarks. And then the other benchmark that we do is the New York City taxi demo benchmark. So this started off with a blogger a few years ago. He started creating different benchmarks. So we recently ran one with the Xeon Phis. We've done some other ones that we'll be releasing shortly as well. And if you go to this particular blog, you'll see that he's done it on a variety of different other solutions, like Redshift, you name it, other different database solutions, and he's benchmarked them all. So once again, it's kind of, he's run them himself, so it's not like we're cooking the books to make ourselves look good. He's been able to verify it. So it's a good way of just showing kind of performance we can get. As I mentioned, we do have a free version of KDB Plus for non-commercial use. You can go to kx.com, which is our website, pretty short, pretty easy to remember. You can just give an email address. It doesn't even have to be a real one, but please put in a real one for our marketing team. So we've got builds available for Windows, Linux, both on ARM and regular x86, and then we got OS X build. So KDB Plus, as I mentioned, is a pure software solution. So that's we also have an academic license as well, and indeed they're actually using it, I believe, in Carnegie Mellon for in New York for their financial engineering class. So we do give free full 64-bit versions available to academic institutions. So if you're interested in that, come speak to me afterwards. Or we also have an academic page on our website as well. For developers then, there's a pretty cool website called Codedoccom. So Kdbcom is kind of like the commercial website, so if you want to see some of our other offerings on top of the database as well. But we've also got this Code.kdbcom. So if you want to start learning the language or look at white papers or learn all of these different functions and see, say examples of the functions and how they work with edge cases, like say nulls and infinities and things like that. And this is really, really useful. We've put a lot of work into it, so we're quite proud of it. And there's also a Google group you can join as well. It has about, I think it's 14 or 1,500 members. So you can go there, ask a question. Oh, like I have this query, I want to make it a bit faster, or I have this library, I'm having trouble. It's a very responsive community. People, answer questions very, very quickly. And we at KX, we monitor it ourselves. So if a question goes unanswered, we'll make sure that it gets answered for you. And there's also a GitHub repository as well. There's 2 GitHub repositories. One is a community repository where we basically scour GitHub once a month, and we take all of the libraries that have been written to integrate with KDB+, and we just gather them all together in an index. And then we have our own GitHub repository at KX, which are kind of like KX approved libraries. So say our C# API or C++ API, etc. So these libraries are pretty cool. There's visual tools built on top of KDB, some which we have ourselves as well. We have our own visual tools. And we have a variety of meetups throughout the world as well. So if you go to kx.meetup.com, we got meetups everywhere. In New York, we have one every month, and we got like 2 or 3 speakers. So it's pretty cool. And then there's 2 books available. We actually recently purchased the rights for Q for Mortals, and that's actually now been fully put on the Codedoccom site that I mentioned. So you can get an electronic version, but you can still get the print version as well. So that's a really nuts to bolts guide of how to learn a Q language from start to finish. It's very, very well written. And then the second book is called Q Tips. It's written by a guy called Nick Saris, who works for a customer of ours. And that's very much more from an implementation side of things. So he shows you how to build up an actual application or system using KDB+. So they actually complement each other quite well, the 2 books, because if you want to learn a language, you can use the Q for Mortals. But then if you want to get into the more implementation side of things, like how do I build some complex event processing trading type of engine, you can use the Q Tips book. And then that's about it from me. I think I've finished before time, actually. I thought I was going to be over time. Obviously, follow us on Twitter, me on Twitter, or drop me an email. And if you've got any questions. We've also built some tools on top of the database in recent years. So we have a visualization tool called Dashboards tool. And then we've got an integrated development environment called the Analyst tool, which was actually designed by the guys who created the Eclipse IDE. And they're based up in our research labs up in Ottawa and Canada. So we'll be bringing more information about that over the next few months. So the Analyst tool in particular is really cool for data scientists. We have an inbuilt ggplot library, which is written entirely in our Q language. It's completely separate from the R implementation. So that's pretty cool. We have syntax highlighting. So maybe we can come back and do a demo of that someday. But we also have videos available for that as well. So if you don't want this command line environment and you want to use a more traditional user-friendly IDE environment, that's pretty cool. So we recommend taking a look at that. If there's any other questions, feel free to ask away.
All right, let's thank him.
Thank you very much.
We have time for some questions.
So, as Andy mentioned, this is kind of a series of talks we've been hearing about time series databases.
Sure.
So, what is, how does KDB fit in this broader scheme of things? Are you seeing, I maybe don't want to say this on video, but are you seeing, you're winning out over certain things and maybe being challenged in certain segments by other things?
Yeah, I'd say because for years, kind of finance was our bread and butter environment, as it were, and finance I think has been ahead of the curve, especially more from a streaming data perspective, because they've always wanted prices to be in straight away, and now that's why in the last few years I've started to get out into other industries, like we're doing lots of smart meter implementations now, and everything is kind of time series now, which is kind of interesting. I always see people in the last few years we're talking about unstructured data as the next big thing, but to my mind, I think structured data is going to make a massive comeback with all the IoT, industrial IoT, because computers understand structure, computers understand binary data. So the speed with which we've needed to have for finance is now helping us in these other industries. I think one thing as well is a simplified data model, as I say, between say the historical and the real time and the streaming, having that one ecosystem. I think in the last year, if you look at the Gartner reports, where they show that Gartner curve, and now the Hadoop is kind of in that trough of disillusionment at the moment on the curve. I think people are kicking back a bit. They've put in these very expensive Hadoop installations with multiple machines, where all they needed was one machine with maybe 256 gigs of RAM or something like that. So we see that a lot of the things that we've solved in finance, now these other industries are approaching those problems because they're finally getting streaming data. They finally need those low latency response times. So in some ways we feel like we've been a bit ahead of the curve, and they're nice problems to solve. Like there's things like, say, geospatial problems that we're now having to solve. So we're kind of changing around, maybe adding in different data types or putting in different libraries to that effect. But we almost see the industry coming towards us in some ways. But yeah, we're still moving towards the industry in other aspects as well. Like we're doing stuff around unstructured data. Like we're putting together a natural language processing library that's going into that analyst IDE tool that I mentioned, and then stuff like the ggplot. So there's elements of that where there's time series, but we're not just a pure time series database. We can also do relational structure as well. We support foreign key joins, so we're not exclusively a time series database. It is fully relational as well. So we feel we kind of can mix both of those worlds together. But we are very schema oriented, so we're very different from, say, like the schemaless folks, where it's kind of like everything is done, ad hoc on the fly, whereas we're very defined kind of from day one. But you can convert between the data types very easily, as we've seen. So by being schema-like, it doesn't mean we're completely restricted. We can do the conversions pretty quickly. So I don't know if that quite answers your question, or yes and no. Stream of consciousness. I am from Dublin.
Go on paper, like who are your biggest competitors?
Who do you see in POCs?
Yeah, so it depends actually on the industry. So if we go outside of finance, we're probably seeing a lot of the traditional databases like your Oracles and your IBMs, just because that's what those industries are used to, like utilities industry and stuff like that. They kind of didn't have huge data volumes, and they're only now getting into the streaming game. So the relational was perfectly fine for their use cases. It was batch loads from devices at end of day, but now they're getting more streaming. They need that time series capability. And within finance, probably initially our biggest competitor back in the day would have been the relational, but now what we find is oftentimes if you go to, say, like hedge funds and prop shops, it will actually be home-baked solutions built on flat file systems. So like something just written purely in HDF5 or something like that, where they just want a flat file solution. But what happens there when we find we're winning out there is the fact that we have a fully complete programming system. Whereas what happens with those other systems, the flat file systems, is they're fine if you've got one very strict kind of use case that you're adhering to. But if you want to try and maybe look at your data in a different way, like we want to run back testing and not just streaming real-time data, then they find they get a bit of a problem. So by being a general programming system and having this fully Turing complete programming language on top, we offer that flexibility within the language. It's a programming and analytics environment as well, whereas the flat file systems are great, but maybe for one very, very strict use case. And so that's what we find we come up against. We hear people talking about other time series databases as well. But to be honest, the speed and performance, I think by just being in finance, we've had that speed and performance. And that's really been, our modus operandi from day one has been about speed, performance, and elegance, really. So like the notation of the language, which it's not for everybody necessarily, but that's why we have these open source APIs built on top of the database as well. So what a lot of people will do is, they'll do a lot of the heavy lifting, these large aggregate queries in KDB, and then they'll push that subset of data maybe into their machine learning libraries or their Python routines, because obviously those languages aren't necessarily built for big data, like real big data per se. So yeah, so it's kind of a mixture. It really depends on the industry. We come across the traditional relational databases, and then we just come across hack together flat file systems. So yeah, it's very interesting. You go different industries of completely different competitions and stuff like that. So.
Can you talk a little bit about like the system architecture, like how are you guys managing memory? What's the runtime look like?
Sure. So we support garbage collection. So you can get rid of garbage collection. So it's configurable. So you can have immediate mode where it does garbage collection automatically, or you can turn it off completely, or you can also do it where it's manually garbage collected. So that's quite nice as well. You offer that flexibility. So obviously, if people are doing very low latency stuff, the last thing they want is garbage collection to hit in and take advantage of that. So and the memory allocation is done via buddy memory mapping. So it's the powers of 2. So it's a relatively simplified memory model, not necessarily the most efficient, but it's all basically about speed. So it was basically the fastest and most elegant memory model we could put together for the performance that we were trying to get. So certainly there probably are better memory allocation models. And for the on-disk data, we use memory mapping techniques. So we memory map the data, and then we'll actually read only the subsection of those files from the page into memory, so we don't necessarily have to read the entire column. And the compression works on the individual file level. So you could compress maybe an individual column for an individual day, so you can get very granular with the compression as well. And as I mentioned, you can use tiered storage, so a lot of our customers will use is maybe for the last week's worth of data, they'll leave it uncompressed in a very fast local, say like SSD or NVMe, or maybe sometime down the line they might even use one of these Optane or 3D NAND devices that are coming out from Intel. But then the older data, then they might compress it and throw it down on a SAN or a NAS type of file system. But to the end user, it just looks like one monolithic database. So the compression and decompression is taken care of by KDB Plus itself. The select statement looks exactly the same whether the data is uncompressed or compressed. So that's one nice thing, is the architecture can be multi-tiered architecture. So that's why it can get these huge database installations, multi-petabyte database instances. We can also map the entire database as well in advance. So you can map, I think it's upwards of 128 terabytes or 256 terabytes, give or take. Something is one or the other, I can't remember exactly which. So you can actually do that in advance, so you can create all of your maps. So then, obviously your virtual memory space is very, very large rather than your real memory space. So that means we can take advantage of the memory mapping down. So the queries are always executed in memory, so you page fault the data in, execute the data in memory. So as I mentioned, the data in memory and the data on disk is essentially in the same format. Typically, though, when we spill out to disk, we usually reorder the data. So when the data is in memory, it's usually time ordered when we're using that, say, Lambda architecture style diagram that we had earlier. I'll just go back to it. So when the data is coming in, like in a real-time database, it's usually ordered by time, because obviously if you try to reorder the data by, say, ticker symbol after every insert, you just kill your performance. So the data in memory is usually ordered by time in this streaming type of a system. And then on disk, what we typically do is we reorder the data. And because most queries from a historical database perspective are maybe research style queries, like maybe one particular symbol or one particular range of stock symbols that we're looking at. So that means that it lends itself much better for doing sequential disk seeks. So if you think about just a traditional spindle, if all of your data from Microsoft is held contiguously together and you're only doing an average price for Microsoft for yesterday, it will only go in and it will memory map only the columns that you're selecting, so it will leave any other columns untouched. We'll memory map those files, and then it will only do sequential disk seeks for only that area of the file that corresponds to Microsoft. So it basically reads as little amount of data as possible. So that's one of the nice things. So you can take care of things. You can look at things like read ahead and stuff like that to actually page fault the data and buffer the data into memory ahead. So it's really nice for sequential style workloads. And that model lends itself even better then when you start working with flash-based devices as well. So it's a kind of a natural fit to our model.
You're letting the OS manage what comes in and out.
Exactly. Effectively. Yeah. So the caching is all actually managed by the OS. So as I say, it's all just simple system calls, open and map, close, etc. So
sort of related to my next question is sort of related to that. What did you do to get it down to 500 kilobytes? Is there any
Is our own? We have our own stylized C code, but it's just. We've had several developers working on it, and it's a relatively small bunch of developers that have worked on it, so everybody knows it very. It's several files.
How do you actually work on KDB now?
It's probably about 5 to 7 developers actively. So it's always been a relatively small workload. So that just means that everybody can collaborate very easily. I mean, they always say, I think, isn't it, that 7 to 8 team members, once you go beyond that, you see the productivity drops. So everybody knows the code base, very, very intimately, so they can really everything's very, very finely tuned. So for example, in the latest version we released last year, or earlier this year, version 3.5, we put in a fully fleshed debugger. We had a quasi debugger before. So that actually putting that in, it involved, very, forensically going through the entire code base. But by virtue of the fact that the code base is so small, small that we can actually make these changes very flexibly and very easily. And it's also very nice from our customer's perspective, because if there's a bug found, we can usually fix it within a matter of minutes, and we'll have a bug fix out later that day. So from a customer support kind of perspective, everybody talks about our customer support is fantastic. And the code base actually lends itself to that, rather than having this massive code base and millions of different types of tests. We still have quite a lot of tests that we run obviously on the database, but by having the code base so small, just you keep your instructions nearer to the cache as well. It's to do with pipelining and stuff like that too. So yeah.
Any other questions?
So do you do usual types of things, like if I've got multiple streaming queries and there's some factor of what they're computing that can be factored out, you do that kind of thing?
So you can have multiple attributes, those like indices that we can have on different columns. But as I say, we typically only take advantage of one attribute in a given query, because you're going to reduce your size set so much by using the first attribute that the secondary. So secondary indices aren't really supported as such. But with the streaming query engines, we can support multiples of those, because it's just basically just file descriptors of the OS. So you can support 1,000, and I think it's 22 or something like that within the operating system. So you can spin up multiple of these streaming query engines. That's why I put multiple of them in here. But they don't necessarily need to be Q code as well. What we often find is people might have a C++ trading engine that will just be subscribing for price data from our ticker plant or the events engine, as it were. So it can be any type of language that could be written in the streaming query engine.
There's no optimizations you do across.
There are. So one optimization is you can potentially bulk publish. So that the events engine can do single publishing or can do bulk publishing. And because we're a vector-based database, we use one mem copy per column. So that means then, whether it's almost like 1,000 records or 1,000,000 records, and because of the way we buffer data, the throughput, it's a throughput versus latency thing. We can get really, really good throughput by bulking up the data. So say rather than publishing instantaneously, we'll maybe publish out every 100 milliseconds or every 1 second, and you get way, way better throughput then. So we have examples that we show in some of our workshops for, even from Java, you get a 15 to 20x, performance improvement by actually bulking the data together. And so things like that you can do, which can help with the stream and query performance. So once again, it's it's a thing of, are you throughput sensitive or are you latency sensitive? Oftentimes as well, what we sometimes find is you can have what we call a chained events engine. And what the chained events engine will do is it will subscribe to the main events engine, but it will actually start buffering the data. So the main events engine can publish the data as it gets it. But then say the chained events engine can then buffer the data, and then that might maybe push it down to say a screen. Because obviously you don't need a screen to be updating 1,000,000 times per second, but maybe twice a second or something like that. So that's where you can start getting into these, and you can start chaining all of these together. The real-time database could even be a subscriber. It's all just logic written in the Q language, so you can have much more complex infrastructures. We also have the ideas of gateway processes as well, and what a gateway process might do is it might sit in between the historical database and real-time database. So say if you don't care whether the data was in today or yesterday, it will just do the query rerouting for you and stuff like that. Or it can also do it over multiple machines or multiple regions as well, which can be a case with a lot of our financial institutions where they'll have data held locally, but then they want to give one kind of data warehouse feel. So you can have these gateways and load balancers, and once again, they're all written in the Q language as well. So you can get, because it's a full programming language and not just SQL, you can kind of write whatever you want. So,
all right, let's thank Fintan again.
Thank you very much.